Learn how to take your simulation models from Simulink to C++ by using code generation tools. This will let you build high-performance C++ engineering applications leveraging Simulink to speed up the development process. Let's begin. Let's say you have made a Simulink model. So this can be a flight control system design. It can be some aerodynamics toolbox. It could be some flight simulation. You have a bunch of inputs and a bunch of outputs, right? The idea is that you have to convert your Simulink code into a C++ file. For those of you who don't know, Simulink and MATLAB is actually built on top of C++. When you convert your code or your model into a C++ class, you will be able to initialize it, set the inputs step, and then get the outputs. Let's talk about these four methods here briefly. When you call initialize, it'll normally set the solver and the time step, right? Because Simulink has like so many solvers like Euler's method, RK fourth order, and so on. You need to first initialize the solver correctly. The next thing you do is set the inputs. And this will be the same thing as passing the inputs from Simulink itself with a signal line. The next method is the most important, and that's called step. So imagine your Simulink model wants to run for, let's say, 5 seconds with a 1 second delta t, right? So the time step is 1 second. That means it'll run 5 times. To achieve the same thing in C++, you have to call the step 5 times because that'll be one time step. Lastly, you have to get the outputs. Now, if the outputs will change with time, which is almost everything, you have to call this get external outputs as many times, right? So, for example, if your inputs stay the same, you only have to set the inputs once. But if the outputs will change with time, you have to call this method here as many times as so. Okay, so here's my first example. I have two inputs. Input 1 goes through a transfer function, which is multiplied by input 2. It is then saturated between two values, and that's the output 1. Input 2 is multiplied by a constant 5, which is passed through an integrator, multiplied by its derivative, and then compared and multiplied once more. The boolean and the product is then summed up, and that becomes your output 2. So quite a simple model here. And let's look at the configuration of it. Here is my test model. One thing you need to understand is that every time you compile something from Simulink to C++ or even MATLAB code, you have to test it end to end because there are bugs in Simulink Coder which you will see. And this will also vary based on the version of MATLAB that you have, right? For me, I did this on a very old version, I think 2015B. So it won't be the same as the new versions, which are much better and bug-free. But in all cases, you still want to test it every time. So in my testbed, I have input 1 is constant value set to 1, and then input 2 is sine of my time value. The reason why is, in many cases, your models will pass if the inputs are constant, but you may find issues if they change with time. And the whole point of modeling and simulation is to examine inputs that change with time for very complex calculations. So that's why my input 2 here is sine of t. I pass the values to my workspace like so, and then I can also display them here. My simulation runs for 1 second at a time step of 0.01 seconds. As you can see, my solver is set to ODE4 and my fixed time step is 0.01. You have to know this before you compile your code because many people, they just compile it without checking the solver. You won't realize it till after, right? So be sure you understand your model fully before compiling it, and this especially includes the solver configuration. So before you compile your model, be sure to check the code generation settings. In my case, I have a C++ class. This can also be a function if you wish, but most people use a class. It looks much better. I would like to support numbers that may not be finite, so infinity for example, and that's why I have the support non-finite numbers checked. Next thing is to disable mat file logging. If you are building a C++ application independently, then this can be off. Next is to check your build here. So in my case, it is set to faster runs. You can also have faster builds, but if you want to optimize the speed, be sure to check faster runs. And then my language is C++. You can also choose C, but most people nowadays use C++ anyway. So when I compile my model, you can see it done over here. So I just build the model from the code option on the top, and based on what version of MATLAB you have, you will see a bit of a different UI. But if you build it, you should wait a bit. It takes a bit of time, and you may have some errors. In my case, I don't have some mex file, so it comes up, but at the same time, all the files are there. And to check this, go to where your file is saved, and you should see a folder called your file name, get RTW. So RTW stands for real-time workshop, and that's your converted code in C++. When you open the folder, be sure to delete any files which are not a C++ file. So for example, .txt, .mat, those can be deleted. And now you have all the files there to start building your application. So before we do the exciting stuff and build our application, we must understand the files which are given to you by Simulink Code Generation. They can be broken up into two categories. The ones on the left are given by coder each time you compile a model. So every time you press build, it'll give you those files, and some of them are multi-word types: RT non-finite, RT get infinity, RT get nan, and RT model. If your model is more complex and has a lot more things in it, then you may have more there. The ones on the right are not given to you by code generation, and you will not see them when you compile the model. You have to get them from your MATLAB installation. You might be thinking, okay, how do I know that those are the files which I need, right? I want you to guess the answer, and I will tell you the answer soon, but just think about C++ and how those files are there, or they should be there. Like think about how C++ works and how I know those file names. And don't worry, you will see the answer in a bit. But those files on the right, those can be found in your MATLAB installation, and whether you have Windows or Mac, they might be in different locations, but you will always see them where your MATLAB is installed. The way I will arrange my files is like so. Now this can be up to you based on your project and what your requirements are, but the common files are kept in a common folder. Each time I compile a model, I will save those in individual include and src folders. So if I compile, let's say, two models, model 1, model 2, I can save them separately like this here. The build system which I will use is CMake. CMake is very popular. I do recommend it for this. I have my main CPP file which will call those files here. That's my application here. And I will store my exe file in a folder called build and release. And you will see why in a bit. So many of you who work on C++, you may be used to doing everything in VS Code or Visual Studio, but I think it's more professional to use CMake, as it's a very common tool for building. The more files you add to your project, the more complex it'll get, and CMake makes things a lot easier. So now let's go into the code itself, and I will show you how example 1 can be run in C++. Okay, here is my VS Code setup, and let's go over those folders now and examine the code that is given to you. Starting off with common, we have multi-word types, and this will just have a bunch of struct type definitions which you will use in your file there for integers, unsigned integers, doubles, floats, and more. The next one is RT non-finite for numbers which may be infinity. Same with RT get inf. And let's look at these includes here. So this was my answer to the question which I had asked before to guess how I know what files I need which are not given to you but are present in your MATLAB installation. So let's look at that. If I go into my rtw types.h, you will see that it includes these two, and that's how I know that I need both of them. And although they are not given to you, you must find them in your MATLAB package. The next one is rtmodel.h, And this file you will most likely have to change if you compile, let's say, multiple files and they have slightly different definitions. You have to merge them into the one common here. So every time you compile a model, please check. I would say just check all these files and be sure that they match what's given to you by a previous model. And if there is a bit of differences, if you have more in another one, just combine them into one here. The next one is RTW continuous, and this is used for continuous time systems, especially in the solver and the continuous. Please don't change anything because these files are needed to run. The next one is RTW types. In this file also you may have multiple definitions if you had compiled more than one model, and just please merge them here like so. The next one is SimStruct types. Since I had used MATLAB 2015, I did have to use it, but if you have a new version of MATLAB, you may not need this file, so just please check as so. And lastly, I have TMW types. And this has just more definitions in there, especially macros, as you can see here, for different variable types like doubles and booleans and so on. Let's look at my files for my example one. So the files will be called your model _ private.h _ types and your source and your h file respectively. So let's go into these now, right? Let's see how they are assembled. In the private file, I just have more definitions. In my types file, the same thing here once again. And here is my class file. So this one includes a bunch of other files which are found in the common folder and your MATLAB installation. Let's go into where my class is defined, right? Or you can just search for it. Okay, it's over there. So here's my model code in C++. It's defined as a class with public variables for inputs and the outputs. If you have a new version of MATLAB, these two will be private, and you will have available these methods for you. So anyway, so let's look at the method. So that's to initialize it, step, and then terminate. I also have my constructor and my destructor. So when my program gets called, my model is instantiated, it calls the constructor, of course, and then when it gets destroyed, it calls my destructor here. And here are my private variables. If I go into my struct here, my parameters, let's take a look at that. So in my file, I had set my saturation to 12 and -12. And you can see the values being stored over there, right? So you see how it stores everything here. So if your model has a bunch of constant blocks, integer blocks, it'll take whatever number is there and save it here. So here my constant value was set to 5, if you recall. Let's go in my CVP file. And this is also super long. So this method will do the continuous time for the RK4. And you see how if you look at this very carefully, it'll match the RK4 solver. So it does a step size and then just does it 4 times here and then gets the average of everything, dividing it by 6. I have my method to set the inputs and to get the outputs. So I just pass in my struct and then set the inputs there and then get the outputs here. Here is the most important function, the step. So this will do one time step here. So I would say don't look at this in too much of detail, because if you have a big model, it'll be super large. In this model, I had experienced bugs, and that's why I have this debug statement over here. But I believe since I'm using a very old MATLAB version, I do have this issue, but for you, it should not be the case at all. And then I have more methods here, like find the derivatives, initialize. That's the one you call before you start your simulation. And then I just put a bunch of statements over here. Just some print statements so I know that the model works. I would recommend you also do this too. And here are my constant values. So, I had said before that I have my saturation, my derivatives, and my integrators. Those are stored over here. So all my initial conditions, which are not inputs or outputs, for example, 12 and 12 here, 5 minus 5. For my transfer function, it was 1 over s plus 5. So those are stored over here. I also put print statements in my constructor and my destructor. I would say I do recommend to use these print statements just for logging and to debug everything. And once you push your code to production, that's when you can just comment them out. Okay, so with that being done, let's look at my testing file. So this here is my application that will call example1 for now. The first thing I do is instantiate my class as a unique pointer. I set my inputs and my outputs there. I call my initialize step. And then I do the same thing I did in Simulink. So I ran it for 1 second with the 0.01 time step, and that's over here. I set my input 1 and my input 2, which match my MATLAB testbed. I then call step, and then I just print the outputs here. So you can see how it's done very systematically. Instantiate your model, define the inputs, set the inputs, step, and then call the outputs. If your inputs change with time, they have to be done inside the for loop, obviously. Since I want to see what my outputs are, I log them here at the end. Let's now build this example and see what it looks like. So before I build my example, let's look at the CMake file. I'm using version 3.16. My project name will be testing app. I set my C++ to version 14.0. I include my example1 only because in this case I'm just compiling example1 in my app. If I had example1, example2, multiple models, then just include all those folders here respectively. Same with this source files variable. Just include everything that you need. In my case, I have my common folder. So all the CPP files inside common and my example1.cpp inside example1 source. Lastly, I want my exe file to end up inside this release folder here. So that's why I have my project source directory /build/release. And that's where my output will be. Lastly, I call my executable run this, and then my file is called testing. So that's the one I'm compiling. I also have to include for the linker my source files here. So that's the variable name, and it just gets passed in like so. Okay, let's build it and see what we get. So you have to drag the build folder and open it inside a new terminal. The commands will be CMake and then CMake build dot. So it builds it over there, and let's run it and see what we get here. So release. Okay, let's take a look at this output in detail. We can see that when I create my object of my example1 model, it calls the constructor. Why do I know this? Because I have my output here saying constructor called. The next thing I did was call my initialize function, as you can see over here, and it's called it there. And then take a look at this here. Remember in my step method, I had put my output statements, product2 and the boolean, and you see how it's called 4 times every time step? That's because of my solver. The RK fourth order solver calls it 4 times because there are 4 minor time steps, and every time you do it, it has to call step. So one call for step will actually call the same thing recursively 4 times, right? Because you see, look here, every time step, like time step 0, time step 0.01, it's called 4 times here. Let's look at the output now. Let's compare the output at time equals 1 second to what I had in MATLAB. You see the output 1 is not too bad, right? It's like close to its final value. But look at the output 2, it's 0. Now you might be thinking that, okay, that's wrong. And it is wrong, right? But take a look at the values of product2 and boolean here. I want you to sum these up and see what you get. It'll be 7.18. Now the value from MATLAB was close to that. So you see how there's a mistake in the code generated, but you know how to get the correct value. For example, the value for output 2 should be this product 2 plus this boolean. That's it. And if you look at the Simulink model, you can see exactly that when you sum those two up, you should get what you had in MATLAB. But for some reason, Simulink Coder made a mistake and it gave you the wrong output here. The variable y.output2 was set to 0. So you see how the power of debugging comes into play here. I do encourage all of you to actually debug your code generated files, because you do need to actually understand C++ to a good level to be able to work with this, especially to catching bugs, right? Because a Simulink coder is not perfect, even though it's gotten better over the years. And this is a prime example of knowing how to debug and finding the right solution. So with that being said, let's now look at example 2. Okay, so for example 2, I did a little more interesting problem. It's a bit more interesting. I'm using the Aerospace toolbox from Simulink, and I have a 3 degree of freedom dynamic model where my inputs are the forces in the x and z direction along with the moment. The gravity is set to 9.81 as a constant. I also have my outputs here, which are the pitch angle, my angular velocity, the angular acceleration, the position in xz, my velocity in forward and down, along with my accelerations too. So we can see that this is very typical for a 3DOF simulation. When I expand the file, we can see the exact calculations here. So it does a bunch of calculations inside. It'll get the force, the mass, and the inertia, and then it gets the pitching moment rate, which is then integrated to get the angle here. So the acceleration becomes the angular velocity, which then becomes the angle, and then that'll be the outputs here respectively. We can see that you can get the speeds as well, and then get it to the earth axis. So that's the speeds in the correct reference frame. When you have the velocity in the inertial frame, you can then integrate that to get the x and z location. For my test bed, I have these inputs here. I've actually not used gravity because that's a constant. My forces are 4 and 7 in the x and z respectively, and the moment is 0.01. And let's look at the outputs after 5 seconds. They can be seen on the display here on the right. Now let's build what we have and compare the values one more time. Okay, so going into our converted code, I followed the same process as I did for example 1. Let's look at the file for example 2, and when I go into my class definition, we can see that the inputs are defined over here. And even for example 1, the names will always match the input names. So whatever you type in MATLAB and the Simulink blocks, those will transfer over here. So we can see that the comments are given to you. So root is your Simulink model, the root file. And then when you go inside the model, you will see these inputs which I had put and they match here. So that's for the inputs, and same goes for the outputs too. Since we have two outputs for the positions and the velocities and so on, it's an array of 2. And this is a C-style array, it's not a vector. So a Simulink coder at this time does not use the STL template, it just C-style everything. And that's because it's meant to be for fixed size values, where this is meant to be a constant. So keep this in mind. And we can see that there are a lot more parameters here, of course. The value for gravity I had set to 9.81, and you can see that it's commented as 9.81 over here. Let's go in the class file. We can see that the value of 9.81 is in the parameters. It's stored over there because I set it to be a constant, of course. I did the same thing here where I put statements for initialized and terminated as well. This one will have a lot bigger step method because obviously the calculations are more involved and there's a lot more stuff going on. Okay, in my testing file, I have the exact same setup. I define my pointer object here. I then define my inputs and the outputs. So I first initialize it, and this time I can do my inputs outside the for loop because it's constant, so it'll always stay the same, 4, 7, and 0.01 respectively. And then lastly, I check the outputs over here. So now let's build it and see what we get. Once more, let's double check my CMake file. Since I'm only compiling example 2 and not example 1, I've only included the folders for example 2 over here. And then everything else is the same. Okay, let's build this. If you want to build multiple times, you can, but be sure to delete the CMake hash file every time. Okay, let's rebuild it now. So same process, open the terminal here, and let's do CMake, and then CMake build. So it took a bit longer, of course, but it's still built at the end. Going to release, and let's run this file here. So let's take a look at this fully one more time. Let's go all the way up. This time I didn't put any print statements in my step function. I just call the outputs here. So it calls constructor, that's perfect, initialized, and then you have all your time steps here. So in this case, I had a time step of 0.05 seconds and an overall time of 5 seconds. So let's take a look at the outputs here. Comparing it to MATLAB, it's pretty decent, especially for the angles and the angular velocity, angular acceleration. And at the end, it calls the destructor. So that's practically it for intro to Simulink Code Generation. Now, the way you build your examples will not be the same as mine. You may have different applications and different examples, but it's very powerful, this feature. You can actually build large scale, C++ apps right from scratch, and then you can integrate your Simulink models into such a tool where you can just build very cool things for your projects and also for academia as well as industry. So I hope you learned something new, and thank you for watching. I'll see you all in the next video. Take care. Have a good day. Bye.